case, now when light travels from air to glass and then glass to air. Okay. Now light is traveling through air. Okay, obliquely. Okay, because the case where the light is traveling obliquely, and then the point, okay, where it strikes the surface of separation between these two media, okay, that is called the point of incidence. Okay, and this ray of light which is traveling through air, now it is called the incident ray. And then a normal is drawn to the point of incidence O, and it is called the normal, and we'll denote this by mm prime. Okay. Now let's compare the speed of light in air and glass. The speed of light in air is more compared to that of glass. Okay. So what happens? Now this will be called what? An optically rarer medium, and this optically denser medium. Okay. Okay, by comparing these two, then the ray of light, when it travels from rarer to denser, from rarer to denser, it will always bend towards the normal, and then you extend this ray of light. Okay. Now this ray of light, okay, which bends, okay, as a result of refraction, this is called the refractive ray. This is called the refractive ray. And then again, okay, it's traveling through, this ray of light is traveling through glass, and then it reaches what? The surface of separation between glass and air. The point where it strikes the surface of separation, that is also called the point of incidence, but we'll denote it by O prime. And then a perpendicular is drawn through this point of incidence, okay, and denoted by N prime. Okay. Any perpendicular line drawn to the point of incidence is called the normal. Okay. And then now let's see. Okay, compare again glass and air. Speed of light in air is more than that of glass. So this will be rarer and this will be denser. Okay. So when light travels from denser to rarer medium, what happens to the ray of light? Okay. The ray of light, okay, as a result of refraction, it will bend away from the normal. Okay. And this, okay, this refracted ray, however, will be called the inversion ray. Okay. It's called the inversion ray. Then the angle which the incident ray makes with the normal, this is called the angle of incidence, denoted by angle I. Then the angle which the refracted ray makes with the normal, it is called the angle of refraction, denoted by angle R. And this angle, however, which the inversion ray makes with the normal, it is called the angle of emergence, denoted by angle E. And this normal, okay, mm prime and nn prime, they are parallel. So what happens to this? They are equal. Okay, so this value it will be as well angle R. Okay. Now next, okay, I'll be doing this laws of refraction of light. Okay. Now the first law states that at the point of incidence, the incident ray, the refracted ray, and normal all lie in the same plane. Just like the second law of reflection of light, okay, that means that if you pass, okay, a plane of paper through this, okay, incident ray, okay, the refracted ray and normal, they will all lie in the same plane. Means that they will pass through this. Okay, and then next is this one, this second one, very important. It says that the ratio, okay, ratio divide the sine of the angle of incidence in one medium to the angle, to the sine of angle of refraction in another medium is constant for a given pair of media. Means that if we try to take any pair of media, okay, this ratio, okay, it will always be constant. Okay. For example, if you have taken the first medium to be air and the second medium to be water, or let's say water and air also. Now, no matter what the value of I and R, if you have taken the ratio, the value will always be constant. Okay. Suppose if you divide, okay, you get 1.40. Okay, 1.40. Then for different values of I and R, sometimes you will get 1.40 exactly or near 1.40. Okay, like sometimes 1.39 or 1.41. Okay, so this is a very important law. Okay, and it was found by the physicist, okay, Snell, and hence known as the Snell's law of refraction. Okay. So light travels from air to glass. Okay. It bends towards normal, and from glass to air, bends away from the normal. Okay. As a result, because air is rarer, optically rare medium, and glass is optically denser medium. Now, okay, because of the phenomenon, okay, called refraction of light, okay, there is, okay, this bending of ray of light. Okay, just like I've told you, because the speed of light is different in different medium. Okay, and we have observed that, okay, that speed and wavelength it change. Okay, when light travels from into different media. Okay, but frequency remains the same. Okay, frequency remains the same. Now, okay, suppose if there was no refraction. Okay, imagine if there was no refraction and there was no glass. Okay, obviously, suppose if there was no glass. Okay, then this incident ray will be traveling in its usual path, right? The straight path. Okay, but since, okay, there is this medium glass which is obstructing. Okay, so as a result of refraction, it gets bent. Okay, okay, and it gets bent. Okay, twice. Okay, in this case, and this shift. Okay, this perpendicular shift. Okay. The perpendicular shift between this original, okay, incident ray, okay, the path, okay, traveled by the incident ray, and this emergent ray. Now this is known as the lateral displacement. Okay. Otherwise, it is the perpendicular distance between the original path, okay, of the incident ray and the emergent ray. Okay, that is known as the lateral displacement. Okay, and it varies according to the change in angle of incidence, according to the thickness of the theory. Then so now we'll be doing about this very important term known as refractive index. So what is refractive index of a medium? Okay? And by knowing the refractive index of a medium, we are able to know, okay, speed of light will refract more in which medium. Okay, suppose if I know the refractive index of glass and water, then I'll be able to tell, okay, in which of these two medium, okay, light will be bending more. Okay, so that is why, okay, refractive index, it is a term, okay, which is used, okay, for telling, okay, which of these materials, okay, will be refracting more light, okay, but after comparing, okay. Then, okay, mathematically, okay, so what is refractive index, okay, of a medium, okay. Now, from Snell's law of refraction of light, okay, this ratio of the sine of the angle of incidence of first medium to the sine of the angle of refraction in the other medium, it is a constant. And this constant, it is the refractive index, which is denoted by mu. Okay? And it depends, okay? It depends what? Suppose the first medium it is glass. Okay? And the second medium is water. Okay? So the value of this refractive index, however, it is of water with respect to glass. Okay? So mu 2:1:2. Right? Okay? Means suppose, however, okay, this is for water in comparison to glass. However, if I take water as the second medium and air as the first medium, the value also will be different. Okay, so for different media, okay, the refractive index also will be different. So now we'll be doing about refractive index of a medium. Okay. Now from Snell's law of refraction of light, okay, the ratio of the sine of the angle of incidence of the first medium now to the sine of the angle of refraction in the second medium, okay, it is a constant. Now this constant ratio is actually the refractive index of the second medium with respect to the first. Remember, of the second medium with respect to the first. Okay. So for example, if light travels from glass to air, then the refractive index, which is denoted by mu or n, okay, it is actually of water with respect to glass. Okay. Now this designation shows that it is traveling from glass to water, but actually it is the value of water with respect to glass, means you're comparing of water with respect to glass. But in this case, it is a refractive index of water with respect to air. Okay, and the value between these two, okay, will be different. Okay, different. Even though it is of water, no, of second medium with respect to first, so of water. Here also water, but here it is air and here it is water. So N, okay, a refractive index of water with this, with respect to this, and this, sorry, this is glass, okay, refractive index of this, water again with respect to glass, however, will be different. Okay. It will not be the same. Okay, it will vary according to the given pair of media. Okay, then refractive index of the second medium with respect to the first medium also. Okay, mathematically it can be expressed as the speed of light in P, means that when it travels, okay, when light travels from P and then to Q, then the refractive index also can be expressed as speed of light in P divided by speed of light in Q. However, when the first medium is a vacuum, okay, when first medium is a vacuum, we no longer say refractive index, we call absolute refractive index. So as soon as we say absolute, we understand that the first medium is vacuum. Okay, so speed of light in vacuum, actually you're substituting here, divided by speed of light in the second medium. Okay, whenever we say absolute, okay, we should understand that the first medium is vacuum. So this one we know that speed of light, okay, wave speed, okay, speed of wave, it is equal to wavelength into frequency. Okay, now frequency I told you remains the same, so you substitute in this formula, so you will find that F and F cancel. Okay, so as a result you get this one, wavelength of light in P, wavelength of light in Q. Now this, it is a result of this. Okay, it's a result of this. Okay, so these are the mathematical expression of refractive index. Okay, so to solve problems depending upon what is given in the question, you have to use the formula.